Probabilities. So probability is a number that describes a chance of occurring one or another situation. So we talk about so-called random phenomena like weather, for example, or like flipping a coin. And random means that we do not know exactly what to expect, but we can estimate the probability of occurrence of one outcome or another outcome. So the probability is given as a percentage, as a number. It can be given either as 20% probability of rain tomorrow, or it can be given as a decimal, 0.20, or as a fraction, 1/5. It's all the same, 1/5, 20 hundredths, or 20%. So such a number will give a probability of occurring of this or that outcome. For example, when weather rainy or sunny day probably may have this or that probability. Okay, an experiment is an observation of a random phenomenon, like you flip a coin and you observe whether it is a tail or a head, or you record the weather for several days and you observe the situation, rainy or sunny or temperature or whatever we are going to observe. The different possible results of the experiment are called outcome. When you flip a coin, you have two outcomes, tail or head. When you roll a standard die, six-sided die, you have 6 outcomes. The total set of all possible outcomes is called a sample space. So, for example, rolling a 2 is an outcome, one outcome. Altogether, we have 6 possible outcomes. So this picture represents the sample space of the experiment when you roll one six-sided die. For flipping a coin, we have 2 outcomes in the sample space. When we select an iPhone from a production line and determine whether it's defective or non-defective, we have the sample space containing 2 outcomes, defective or non-defective. So we consider only this feature, only this property of an iPhone. That's why we restrict to 2 outcomes. 2 children are born into a family, and we know the birth order with respect to the gender. Use a tree diagram to help find the sample space. Okay, what is a tree diagram? Okay, we usually start from a point and we draw the branches. So first, when the first child is the first stage of our tree diagram. It can be either a girl or a boy. On the second stage, second child. So we assume that these outcomes are independent. So actually, it is possible that the second child will be also either a girl or a boy. Girl or a boy. And we have two children in the family, and actually we have 4 different outcomes. Girl, 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 boy, boy, girl, boy, boy. We have 4 outcomes in the sample space. So in our experiment, the experiment is 2 children are born in a family, and this experiment has sample space containing 4 outcomes. If 3 children are born to a family, the tree diagram will look like this. So first, we start our experiment. First, the boy or girl is born to a family. Then the second child, boy or girl. Then the third child, boy or girl. We have altogether 8 outcomes. They can be listed as boy, 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 girl, and so on. The situation with the standard card deck is more complicated because there are 52 cards, and listing all the outcomes can be difficult. In our experiment, we select one card from a standard 52 card deck, and then without returning a card to the deck, we select the second card, assuming that the order in which we select the card is important. Okay. In this experiment, the sample space is too large to list all the outcomes. We can use the fundamental counting principle to list all possible outcomes. We perform our experiment in stages as a series of tasks. The first task, we select one card. This is the first stage or first task. Each can be done in 52 ways. The fundamental counting principle. If the first task can be done in A ways, the second task can be done in B ways, and so on, then all tasks can be done in a product of these numbers ways. Drawing the second card is the second task, and so on. Let us consider 2 situations. We draw the second card without replacement, or we draw the second card with a replacement. First stage, we draw the first card. 52 ways to do it. Second card, without replacement, means we have only 51 cards left. So the second card can be drawn in 51 ways. 2 cards can be drawn in 52 times 51 ways. The second situation with replacement. The first card can be drawn in 52 ways, the same. With replacement means that we return the first card back to the deck. So the second card can be drawn again in 52 ways. We draw the first card and return it to the deck. The deck still contains 52 cards, so we have again 52. So 2 cards can be drawn in 52 times 52 ways. So you see the difference between drawing with replacement and without replacement. Okay, let us consider another situation. We roll 2 dice. It's a very good example for a test problem. Rolling the dice, not so many and not so little, not so few outcomes. We roll a standard dice. In your homework, you will have non-standard dice, 10-sided dice, 7-sided dice. Now we consider the standard one, 6-sided die. And the sample space can be represented with a table. So the first number is the showing on the first die. The second number is the showing on the second die. Okay, and here are all possibilities, all possible combinations. So first die can show 1, 2, 3, 4, 5, 6. The second die can show 1, 2, 3, 4, 5, 6. And when we move down from the first line to the last line, we change the number on the first die. When we move to the right, we change the number on the second die. Altogether, we have 36 outcomes, 36 ordered pairs in this experiment. So this is the sample space. we can write here the sum. So if you are interested in the sum, we can write 1 plus 1, 1 plus 2, 2 plus 1, and so on. But there are still 36 outcomes. An event is a subset of the sample space. So, for example, an event can be one die shows a tree, or the first die shows a tree. The first die shows a tree in this line, or the second die shows 5, or 5 on at least one die. So we can, or the sum is 7. A head occurs when we flip a single coin. So the sample space contains consists of 2 outcomes, head and tail, and the single. A head occurs actually includes only one event. The set is just H, just head. 2 girls and 1 boy are born to a family. So actually there are 3 ways to get this. The boy can be either on the first place or on the second, or on the third place in the order. In a family with 3 children, there are more girls than boys. So this is almost the same, but we also include the situation when all the children are boys. So BBB, BBB, and the other 3, the girl happens to be born the first or second or in the third place. Okay, we roll a pair of dice, write each event as a subset of the sample space. A total of 7 occurs. Okay, we need to list all our outcomes, and you will need to do it on the test also. So it is hard to do it in your head. So if you have such a problem, you need to write down the sample space on your scratch paper and to show the event, what outcomes represent the event. So like on this picture, the total of 7. Actually, it is the total that happens the most. So you see in the middle of the line. And we have 6 outcomes, and when we list the 6 outcomes, we can list them like this: 1 and 6, 2 and 5, and so on. The second die shows 4. So the second die shows 4. So the first number is the showing of the first die. The second number is the showing on the second die. So those outcomes show 4 on the second die, and there are 1, 2, 3, 4, 5, 6. 6 outcomes. We can write them as 1 and 4, 2 and 4, 3 and 4, and so on. So 6 outcomes. Another question: at least one of the dice shows a 3. At least one means 3 can be on the first place, or 3 can be on the second place, or 3 can be on the first and on the second place together. So and then there will be 6 plus 6 minus 1, 11 outcomes. 11 outcomes, because we don't want to count this one twice. Okay, so 6 in the line, 6 in the column, and we don't count this in the middle twice. Altogether 11 outcomes. The question can be different. One of the dice shows 2. You see the difference with the previous question? One of the dice shows 2 means not both, one of the dice. So either the second dice or the first dice, but not both. Okay, so for this event we have 5 plus 5, 10 outcomes. 10 outcomes. The total is 8. You have already noticed that the total is the same on a diagonal. So if every diagonal has the same total, so here the total is 3, on this diagonal total is 4, 5, we need 8, yes, and so on. 8 is here. 6 plus 2, 5 plus 3, 4 plus 4, 3 plus 5, 2 plus 6. On this diagonal, we have the total of 8, and we have 1, 2, 3, 4, 5 outcomes. So if the problem asks you to list the outcomes, you list them as I have listed them A and B. But to find the probability, we usually need to know the number of outcomes. So, and this is what I usually ask you on the exam, or this is what you need to find the probability of this outcome. So the number of outcomes in the event. And here's the first definition of empirical probabilities. So the probabilities can be empirical or theoretical. Probability may be based on empirical information, for example, the result of experimental data. Then it is called an empirical probability. Probability can be based on the theoretical information, as with cards or with rolling a fair dice. Then okay, when we have an unfair dice, we can also calculate the probability, but we need to know the exact information about the unfairness. So we can use empirical probability to determine whether the dice is fair or unfair. But okay, we will mostly talk about theoretical probabilities with fair dice or fair card deck, when every outcome is equally likely outcome. But first we talk about empirical, that are determined from the experiment. So we perform an experiment several times, then we estimate the probability of the event E as a fraction. The number of times E occurs divided by the number of times the experiment is performed. So like we flip a coin, and we want to know the probability of getting ahead. For example, we flip a coin 4 times, 3 of them we got a tail, 1 time we got a head. The probability from this experiment is 1/4 and 3/4. Okay, if you know it must be 1/2, but from the experiment it will be this or that. Okay, that's why the result of this experiment depends. Is more reliable when we make more experiments. That's why when we make experiments, we try to involve as many experiments as possible. For example, a pharmaceutical company, of course, they want to have as many experiments as possible. Let us say that, to simplify our calculation, let us say that an experiment is performed 100 times. For example, we test a flu vaccine. Of course, it's too little, but we want to make it simple. Okay, suppose that the flu vaccine was tested 100 times, and the company got 85 cases of no side effects, 13 cases of mild side effects, and 2 cases of severe side effects. What is the probability of getting severe side effects, you see the definition, the number of times the event is now severe side effects, how many times they have occurred, 2 times. So the probability is 2 divided by the total of 100 times. Mild effects, the number of times the situation occurred divided by the total number of experiment, 1300s. And no side effects, the probability of no side effects is 8500s. Another situation, marital status of the population in thousands. So if you randomly pick a man, what is the probability that he is married? Okay, we consider only the line of men's. The total, the sample space is the total number of males. We add, so in some tables you have also the total. I think in the homework you usually have the column with the total numbers. You don't need to add them together, but here we don't have this column, so we add them together. And this is the sample space, 9763. To determine the probability of the event married, now married. Here, this is the event M. 1834,000 men who are married but not separated. The probability will be the fraction, the number of outcomes in the event divided by number of outcomes in the sample space, 9763. And you round as your problem tells you. What is the probability that a randomly picked up married person is a woman? Okay, we need. So the sample space is married person. So here. So we here, if you have this line with a total, just take from this line. So the sample space will be 1834 plus 2488. And the event is a married woman, 2488. So this is how we work with the empirical data. We usually have the probability is given by the table, and we work with these numbers. Okay. More interesting is the counting probabilities that are calculated from theoretical information. For example, we flip 3 fair coins. What is the probability of each outcome in the sample space? The events are equally likely outcomes. So we only can calculate with equally likely outcome, easily calculate with equally likely outcomes. It means the probability of every one outcome is the same. Then we can tell that there are 8 different outcomes, 8 combinations of the letters T and H. Each outcome has a probability 1/8. So the number of outcomes in the event divided by number of outcomes in a sample space, the probability. This is the same formula for counting probability as we have used for empirical probability, but now the number of outcomes and the number of elements in the sample space is given by the theory. So 8 combinations, 8 possible combinations. They are all equally, they have equal right to happen. We flip 4 fair coins. Again, 4 fair coins means every of the 16 combination has the equal chance to occur. So the probability of each one of outcome is 1/16. So if E is an event in a sample space S with all equally likely outcomes. Then the probability is the number of outcomes in the event divided by number of outcomes in the sample space. So I told you that it's the same formulas for empirical probability, but we know these numbers from the theory. What is the probability in a family with 3 children that 2 of the children are girls? Okay, sample space contains 8 outcomes, 8 equally likely outcomes. The event 2 of the children are girls contains 3 outcomes. We can search here in the list. So we have boy, 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 girl, boy, girl, boy, and so on. If you look carefully, so that we have 3 possibilities that there is 1 boy on the first, on the second, on the third place, so 3 outcomes. So the probability, then the probability of this event 2 girls is 3/8. Number of outcomes in the event of a number of outcomes in the sample space. What is the probability that a total of 4 shows when we roll 2 fair dice? Okay, number of outcomes in the sample space is 36. The total is 4 on this diagonal. We have 3 outcomes. So the number of outcomes in the event, 4, divided by number of outcomes in the sample space, the 3/36, or you can divide by 3 numerator and denominator and simplify to 1/12. What is the probability that a total of 8 shows when we roll 2 fair dice? Okay, total of 8. Let me find this diagonal with a total of 8. This is 4, this is 8. So probability will be the number of outcomes in the event over the number of outcomes in the sample space, and both numbers are divisible by 4. Yes, yes, it will be 2/9. Oh, wait a minute. What? Sorry. Sorry. There are 5 outcomes. 5 outcomes. So 5/36. 5/36. Okay. And now a little bit complicated because when we work with cards, 52 cards, to calculate the probabilities, we need to use combination formulas and binomial coefficient. I think it is in chapter 12, binomial coefficient and formulas, but we don't need know much about it. We only need to apply for a couple of problems. We need to apply this combination formula for binomial coefficient. Binomial coefficient can be, for binomial coefficient, we can use any of these notations. So this book, for some reason, uses this one, C of n r, n comma r. Another books use this or that notation. So college algebra book use n/r. And this notation means n factorial divided by r factorial times n minus r factorial. Factorial, you cannot find factorial in your calculator. It just means the product of all numbers 1 through n. So 5 factorial means the product of numbers 1 through 5. So you can use calculator to multiply them, but you cannot find this sign in the calculator. This binomial coefficient or gives the number of possible combinations when we choose R object from a set of N object without regarding the order. Or it gives the number of combinations of N object taken R at a time. For example, if you have 52 cards and you take 5 cards at a time, then N equals to 52 and R equals to 5. Or how many groups of 3 pictures from a set of 5 you can you select to make a custom collage for a Facebook cover. So from the set of 5 means N equals 5. Taken 3 at a time, R equals 3. So combination C of 5 taken 3 at a time will be, so in the numerator you always have the greatest from the two. Let me see where is the second line. And here we have the R factorial and 5 minus 3 factorial. 5 factorial is 1 times 2 times 3 times 4 times 5. 3 factorial is 1 times 2 times 3. And 2 factorial, which is 1 times 2. Okay, and usually you can cancel the 1 factorial from the numerator and 1 from the denominator. How many ways you can select 4-person committee from a set of 10 people? From a set of 10, taken 4 at a time. 10 factorial over 4 factorial, 10 minus 4 factorial. 10 factorial over 4 factorial, 6 factorial. And again, 10 can be represented as 6 factorial times 7, 8, 9, 10 divided by 1, 2, 3, 4, and then you can calculate this. Okay, in our homework, we may find the problem like this. We draw 5 cards randomly from a started deck. What is the probability that we draw one particular hand? Any hand but one. The probability of one particular hand is 1 divided by the number. How many combinations of 5 cards taken taken from 52, and this combination is given by the combination formula, and you can, as usual, you can simplify this, because 52 factorial can be represented as 1 times 2, 47 times 48, 49, 50, 51 times 52, and this first part of this product is actually 47 factorial, which allows to simplify the fraction and to get it, and this allows to get to cancel 47 factorial from the numerator and from the denominator. So accordingly, the probability will be 1 over 2.5 and so on million. So very, very small number, the probability of one particular hand. If you draw 5 card hand from a standard deck, what is the probability that 5 cards are hearts? Okay. This time, the number of outcomes in the event is selecting 5 cards from 13 hearts available. There are 13 hearts in a total, so the combination will be in numerator and in the denominator. In the homework, for those who do not know the composition of a deck, in the problem there is a link to the total deck. So what is the probability of getting a diamond card? Diamonds is one of the suits, so there are 4 suits, therefore the probability of getting a diamond will be 1/4. What is the probability of getting a king or a queen? So there are 13 cards. 2 of them are kings or queens. So on a total there are 13 times 4, 52 cards in a deck. So the probability of getting a king or a queen will be, so you can either consider them. So you, okay, in every suit there are 13 cards. 2 of them are in the event, so it will be 2 over 13. Or you can think as in a whole deck. So there are 2 times 4 king or queen from the total of 52 cards. But this will give you the same 2 over 13. What is the probability of getting a red queen? So there are 4 queens, 2 red queens, and 2 black. Black queens. So the from the total of 52 cards. So the sample space is 52 cards. The probability of getting a red queen will be 2 of 52 or 1/26. Probability of getting a red card. Okay. There are 52 cards, 26 are red, 26 are black cards. So the probability is 26 from 52 or 1/2. So these are the examples of theoretical probability. You must remember that the total probability of a sample space is always 1. So this is the probability of a sample space. Or, so the probability is a number from 0 to 1, probability of an empty space or impossible event is 0, and the maximum possible probability is 1, the probability of a sample space. Okay. And the last thing, that odds is not completely the same as probability. For example, in the family of 3 children, the odds against having all 3 children having the same gender will be 6 to, so 6 different gender to 2 outcomes with the same gender, 6 to 2 or 3 to 1. Yes, but the probability is always the relation to the total. So the probability of having the same gender will be 2 over 8. So the total, in probability we consider the total 8 outcomes. So in some problems in homework, the question is about odds. So here is the difference. Odds is 6 to 2 or 3 to 1. Probability is 2 to 8 or 6 to 8. So there we have a total number of outcomes.